Start? Fine. So, today is the last day, right? We started out 6 days ago. And see, all three of us have been discussing one way or the other properties of electrons. In my set of lectures, I try to focus on the electronic properties of materials in very simple terms, especially keeping the interest of contemporary fascinating subject of nanosystems. So in order to do that, I try to confine myself in simple terms into two-dimensional materials, and therefore we talked about graphene as a prototype example of a 2D material, and it's a nanosystem. And 2D systems have extremely interesting and new phenomena that show up. And so therefore we did the tight binding model. Okay. Remember the first day itself, we motivated the tight binding model. Right? Now, let me just remind you that this is the simplest tight binding model what we wrote down. We sum over all lattice sites, and then you have a site energy, and then you sum over ln m. If you only assume nearest neighbor interaction hopping, then you put angular brackets. You have a hopping terms like TLM. Then you have this kind of projection operators. You take Hermitian aircoin. So in general, these hopping terms will be complex, especially if you put a magnetic field, because we saw that each hopping term will acquire an Aharonov-Bohm phase. Otherwise, it can be also real. And so this is basically the underpinning theme of my set of lectures. Now, to calculate these from first principles, these parameters would require you to have these elaborate theoretical ideas, but you see already, even for a molecule, things can get messy. So I take a physicist approach, very close to experiment, and D.D. Sharma showed that how you can extract these parameters also from spectroscopic measurements. Right? So you stay close to experiments, check if you take those parameters from the experiments, put them in, do some simple calculations, and see if those calculations match with other experiments, and that's the way we progress in this area. And nanosystems then give us more challenging issues, and we'll see soon that our normal notions of three-dimensional materials, even your definition of what you call resistance, what you call conductivity, they all have to be re-looked at when you go to lower and lower dimensional systems. So today, there's a lot of excitement in 2D, in 1D, 0D when you have a dot. And so that's the physics that we want to bring in, where quantum mechanics, of course, plays a very important role. And the other thing that you see, that spectroscopy, of course, is one tool that you shine light from a laser maybe, or X-ray, do photoelectron spectroscopy. But another very important tool for physicists is to apply electric and magnetic fields. The magnetic field, of course, will give rise to magnetism, but we are only talking about orbital part. We have not considered spin, and because we have not considered spin, and we looked at simple Drude theory, in the simple Drude theory, there is no magnetoresistance. The magnetoresistance comes if you have, for instance, impurities in a material. Impurities play a very, very important role, defects, and experimentalists actually want to put in defects, integer Hall effect, and then fractional quantum Hall effect. In those effects, disorder or defects play a very important role. Defects are ubiquitous in nature, they always occur, but you can also, they know how to control these defects, so the defect concentration is actually a handle that you can manipulate in the laboratory. And so the geometry that we consider is one in which the B field comes out of the plane of the paper, plane of the board. This is your y-axis, this is your x-axis. So think of Z as coming out of the plane of the board. So electric and magnetic fields are externally applied fields to probe the system, and you want to look how the system responds. So in the laboratory then, you can manipulate various things. Okay, sorry, I got distracted. So what I wanted to say is that if the impurities also have magnetic spin, coming from the intrinsic spin, all right, then if you have a flow of electrons, then of course the electrons have spin, and you'll have spin-spin scattering process, spin-flip scattering, and that will give rise to another kind of resistance. It is something that I have not considered. Okay? The simple Drude theory that we started out with yesterday, we did not consider this. So, so in the laboratory, in the lab, one can manipulate. So these are control parameters for your, in your experiment. You can manipulate electric field, magnetic field, okay, number of electrons. You can control the number of electrons by changing what are called gate voltages. And of course temperature. Temperature, T, sometimes pressure, P. So these are all your tools. And in IICR campus itself, experimentalists, or my experimental colleagues here, they have these tools here to see various properties in different regimes, right? Not that everybody will have a pressure setup, or everybody will have a magnetic field setup, but it's a combination of all these things that allow you to do things in a very cogent way. So here is this Hall bar that we introduced yesterday, and a Hall bar allows you to make, so you have this two-dimensional sheet of the material, okay, and you apply an electric field to the batteries here, and also magnetic field coming out normal to the plane of the board, so it's normal to the sheet. And so Dr. Pathu Mitra and Dr. Pradeep Thakur, they are experts in this field, so they can correct me if I say anything wrong. And so, you know, your starting point is simple. So actually, today, we should not be rushed. And you must be also tired of after listening to all these lectures. So we will not do much mathematics. Keep things very simple. And I'd like to actually just focus on concepts. So what did we say yesterday? You start writing down the simple Drude theory, which you can find in any elementary book in solid-state physics. So the Drude theory says that you write down the equation of motion of an electron. It has got a mass and it's got a v dot. And so you have a force due to an electric field, a force due to the magnetic field, which is a Lorentz force. Right? And then you have, and that term is actually a very important term. It is not there in Newtonian physics or normal Lagrangian and Hamiltonian physics. You have put that in externally by saying that when electrons move in a material, they get scattered. Okay, due to the scattering can happen due to phonons, due to other defects, due to other electrons, and so the electrons can suffer collisions. The collisions could be elastic collisions or could be inelastic collisions, right? Elastic collisions are the one in which you don't have any change in energy. So elastic collisions are energy conserving. And inelastic collisions in which energy is transferred, so this is energy non-conserving. What's the meaning of energy non-conserving? Because there has to be then some system which will either absorb or give back energy to the system, and so you must have what is called a bath, right, a heat bath. But even if you have elastic collisions, so elastic collision means that energy doesn't change, but the momentum direction would change, right? Sometimes called momentum reversal collisions. So what happens when the momentum changes? An electron is a quantum particle. Though the equation that I'm writing down is fully classical, but I'll indicate where again you see interesting quantum mechanics coming in. So see what happens is the electron is actually a wave. It's a quantum particle. So its wave function is like a plane wave e to the I p dot x. But a collision can change the direction of p. So there is a sudden, because collisions are random, like in a Maxwellian gas. You assume that the electron density to begin with a picture in which it's dilute, so the electrons do not interact much except during collisions, exactly like in a classical kinetic theory of gases. And when they collide, the momentum suddenly gets reversed or altered in direction. The momentum gets altered, the phase of the wave function gets a jolt, random jolt, sudden jolt, and so its phase is randomized. If phase is randomized, then of course you lose, this is called phase relaxation, and you lose some amount of coherence. But you can also have inelastic collisions, and we at this stage are not going to distinguish between whether collisions are elastic or inelastic, but the net result is that you have a term which is written down in terms of what we introduced yesterday called the relaxation time, sometimes called that, or scattering time, or collision time, etc. So this is a conceptual jump, of course, because you have broken time reversal invariance by bringing that term that we discussed quite extensively. This is a term that you cannot derive from usual Lagrangian or Hamiltonian, though again Goldstein, classical mechanics book, which is what we used to use in our MSc days as the book in classical mechanics. In the first chapter itself tells you how you can write down a Rayleigh dissipative function in the Lagrangian and even get dissipative terms. So this is your simple Drude theory. So the physics that is being described by that equation is that if I have a combination of electric and magnetic fields, the electron will of course feel the Coulomb force or the electric force field into the electric field. You feel a Lorentz force, and the Lorentz force is such that that force is normal to the direction of motion because it is V cross B. And so the electrons will not only move in the direction of the electric field, but will also spiral around, and that is responsible for Hall effect, right? That you can have a voltage drop along the direction of the current, but there is also a voltage drop normal to the direction of the current, and that's what you measure experimentally in the VH. So you can measure a longitudinal voltage and you can measure a vertical voltage, and that's the Hall geometry. Okay? And in the process, of course, you have a damping term, and the damping term is given by this. Now, as I said, things of course are not that simple. It's a simple picture.
The Hall geometry you just mentioned, is it the Van der Pol geometry or the
Sorry?
The Hall geometry you just mentioned, is it the Van der Pol geometry specifically?
Van der Pol, I don't know. Partho, can you?
No, it's a Holberg geometry.
Okay, normal Holberg geometry. Okay.
Yeah, I mean,
You can
I
measure
don't know much
from
about
Van der Pol geometry,
Okay.
but this is more accurate.
Okay.
And the other point is that, right, but of course we have to do quantum mechanics. So in quantum mechanics, you don't talk in terms of velocity, but you talk in terms of canonical momentum. And the canonical, so therefore you have, of course, you know, the position is lurking around because, see, this is the first order equation you have written down, but underlying there's also another equation which says that the rate of change of the coordinate is given by the velocity. That's the definition of velocity. So in a sense, you have actually coupled equations in order to get to, you solve the velocity equation, and in order to solve the R equation, you have to go here. But in quantum mechanics, you replace mv dot by momentum. Of course, it's kinematic momentum, and you have to be careful because you know that the kinematic momentum, I mean, you have done it, is replaced by the canonical momentum minus EA over C, where A is the vector potential. I'm not going to discuss the vector potential language here at all. So everything is now gauge independent, there's no gauge dependence. But the point that I want to make is that the momentum and the coordinates, of course, do not commute with each other. So these are now equations of motion for non-commuting operators in quantum mechanics. That's one complication in the problem. And the other complication is that how do you get this dissipative term? So, see, this dissipative term will now also have a feature of what's called quantum dissipation. You have to put the system in contact with a quantum reservoir, like a quantum reservoir could be a bunch of phonons or like bosonic excitations or a bunch of fermions, and they give you different kinds of spectral functions. So this is a very active area of research today, dissipative quantum systems. Now, I also probably have mentioned that the fact that this kind of a term occurs is something very reminiscent of another area called Brownian motion. So the simplest Brownian motion picture that you have, I'm sure you're all familiar with, is that if you have a tall jar and you have, let's say, water, and so these are water molecules, but you're